All right, for our final speaker of the morning session, it's my pleasure to present Russ Tedrake from MIT. Russ has been doing lots of amazing work. Was a reinforcement learning guy for a long time and has moved on to maybe a different approach, which he's going to tell us about today. And I don't want to spoil anything, but he promised that there may be robotic demos after the talk.
I promised that like 2 minutes ago when I was finishing my slides. But
just holding them to it.
Okay, thanks a lot. So these days I am completely focused on thinking about manipulation. And I want to tell you a little bit about my learning, at the very least, about manipulation. And there'll be some learning in there, I promise, too. So I wear two hats now. I'm still at MIT, and I'm teaching at MIT. But I've also, I'm working at TRI, which has got a robotics team. We recruited an extremely strong robotics team to try to make breakthrough technologies that could help people age in place in the home. Okay, and today I get to actually show at least a sneak peek of what some of the manipulation capabilities we've been developing at TRI. Okay, and the example I'll show here, let me just be clear that TRI is not proposing that everybody should have a KUKA in their kitchen. This is just an example of what a hard manipulation task. But imagine you're faced with the problem of putting away the dishes from a very cluttered sink, okay? So into the dishwasher. Now, at first blush, this looks like, maybe to the untrained eye, this looks a lot like a lot of the manipulation videos you'll see online, a lot of them that use learning and everything like this. It's actually much harder because a lot of the demos you see these days will sort of reach in and pick up almost any object. We sort of affectionately call those the pick and drop, right? So it turns out you actually don't need to know that much about the object in order to get your hand around it and pick it up. Just understanding local geometry gets you very, very far. This is trying to do actually much more. You have to understand enough about the object to be able to get it into a desired configuration into the dishwasher. And that actually just pushes the requirements way down the road. And it's been much, much harder, but it's pretty awesome to be working with a strong team on this. So this is just the quick view of it, but this robot is capable of handling quite complex scenes, but doing precise manipulation with the objects that it should understand and discarding the ones it shouldn't understand. And if I can impress on you, the level of robustness that we're interested in at Toyota is not sort of one video. This is something that we hammer on all day long. We have Monte Carlo tests covering this. We know, the 8 most common failure cases. We hammer those down, and tomorrow there'll be 7 most common failure cases. And it's really trying to get to a level of maturity that I was never able to try. It wouldn't be the right thing to try to achieve in academia. So it's super fun. The tasks. Sorry. Next slide. If you look more closely at some of the specific examples, there's some pretty subtle manipulation happening there, whether it's reaching into the sink to get a pretty occluded mug, whether it's grabbing, just open the dishwasher to do this, whether it's grabbing utensils, doing some work to get the utensils. It's a big hand and a small sink, so it sometimes has to do some work to sort of knock things out of the corner. There's a lot of, corner cases, if you will, in this. Finding all of the squirrely cases where the robot, the simple method doesn't work and you have to cover that is an extremely, extremely hard problem, but one that is actually, it's changed the way I view some of the hard problems in robotics. This one played fast, but just it'll even close the dishwasher and actually has a little capacitive sensor on its fingers, on its hand, so it can turn it on, just for fun. Okay, so I can't yet tell you everything about what's happening there, although I'm going to try to tell more about this at RSS. But let me tell you that that simulation is a dominant part of our process. We've made a major investment in simulation, like MO, but separate from MO, including quite rich contact models, and it's actually full stack simulation. So we take sort of a model-based design approach. We have computer game quality rendering, but unlike most computer games, we write it in a way that sort of declares the state of the renderer in a rigorous way, and you can ask, we will eventually provide differentiable, rendering, but to be able to do principled system design on a full stack of manipulation is extremely hard and it's sort of a labor of love, but it's what I believe. Okay, so you might see that and think, of course, that demo is using all the best ideas from control, right? Or maybe it's doing deep RL. Unfortunately, it's not. Even though the rules of the game are clearly given by physics, I think this should clearly fall under the domain of control. And we do have the models, right? But unfortunately, the manipulation problem breaks basically every rigorous, reliable approach that I know for control in important and exciting ways. So this is not supposed to be a downer. This is supposed to be a call to action, okay? So it's sad but true, but basically nobody uses feedback control in manipulation. When you watch these demonstrations, far and away the most common thing you see is the robot will perceive the world, think a lot about maybe a collision-free plan, then close its eyes and go like this, right? And there's only so many times you can watch the robot do this, get a little bit of a perception error, go down, airball, right? And go through the rest of the motion with nothing in its hand that you just think, why don't we have feedback control and manipulation? Okay, so everybody agrees that robustness is the major problem in manipulation, but somehow, unlike every other reasonable engineering discipline, manipulation doesn't have feedback control. Okay, let me be a little bit more precise. It doesn't have what we would consider principled or rigorous or generic approaches to feedback control. So you can find feedback control and manipulation. This is Andy, one of my favorite people in the world, and one of my favorite videos at Boston Dynamics. He's got the robot opening doors, and it's incredibly robust, right? So robust to hockey sticks and other antagonism, right? So there's clearly feedback there. So how can I possibly say that nobody's using feedback? But Andy has carefully and through a lot of work engineered that feedback control with hand-designed controllers. And we've done similar things in the dish loading task. We have incredibly good engineers writing this sort of feedback. I mean, nobody will listen to me if I keep that going. All right, so so it's a real pain point for us, the fact that humans had to write the low-level. The people that we have writing this, Siwan and others, are some of the very best. They can write new feedback controllers extremely quickly, but it's still a pain, right? So when we, through automated testing, find a new failure case, we have to go in and fix it manually, or decide if we have time to fix it manually today, right? And every time we make that fix, we got to make sure we didn't break the 100 other cases we know about, right? It's actually the pain point in our process is not having a way to synthesize the feedback control at the low level, okay? So my goal for today is to tell you why feedback is failing, for me at least, in manipulation, to try to articulate some of the core challenges and show you, hopefully, some progress towards it from the teams, from the students we have at MIT working on this. Okay, so the first problem is basically what Emmo told you about, and I knew Emmo was going to tell you about it, so I get to skip a little bit, and I'm going to tell you the polar opposite version of what Emmo said. But the problem of control for non-smooth mechanics, right? He told you how the gradients are painful, and there's this discovery problem, right? So my version of that is if you look carefully at this, the robot actually, when it's picking up a plate, is one of my favorite tasks. C1 wrote this. It's beautiful. It's actually a very good feedback controller. If you noticed, it was doing a little bit of orientation at the end. It was actually doing some alignment with the point cloud. There's a camera on the wrist. Oh, I just want to make perfectly clear, the demo you saw didn't have motion capture or anything. That was all perception from cameras and depth sensors, and it was sort of the real problem. And this is using contact sensing. It's using the on-the-wrist depth camera to do the alignment, and it's a feedback policy that comes down, touches, reaches, and goes in, okay? But when you're doing a task like that, you have these stiff differential equations where the contact forces are discontinuous or stiff, depending on how you model them. We have no force unless we have contact. Emmo's trick is a way around that, in a good way. But they're often set valued because Coulomb friction is impoverished, but that's our favorite model of friction, and that's a set valued function. Okay, so that leads to these measure differential inclusions or time-stepping linear complementarity problems are the types of things that I knew Emmo was going to tell you about. But I'm not going to talk about that part that Emmo talked about, which is the more global discovery part. Let's say I used Emmo's algorithm or our algorithm to come up with a plan So I have a nominal plan, which means for me both what the robot's going to do and what the plate's going to do, right? And now I want to robustly stabilize it. That's the part that's missing, is this feedback on the fly. Okay, so if you have MPC for contact mechanics, if I were to do the sort of the standard MPC formulation, then the linearization is not enough, as Emma sort of told that story. The linearization doesn't capture even the local dynamics. These are non-smooth. I think the moral equivalent of taking a linearization and stabilizing with LQR is to take a piecewise affine approximation that talks explicitly about the discontinuities and then solving a piecewise affine quadratic regulator, for instance. Okay, so in practice, we actually prefer mixed logical dynamical systems, but just to think about it, you can write it as a piecewise affine system. Okay, so it's almost the LQR problem that Miriam and others have talked about last time, but now we have a piecewise linear system. Okay, so the way you would write that down is as a mixed integer convex optimization. The solution to the piecewise affine contact problem is a mixed integer convex optimization. It would look something like this, but now I've got some discrete variables that encode, some binary variables that encode which of the pieces I'm in right now, okay? MO's version of this, I think, would be to just run the nonlinear trajectory optimization all the time, and differences of opinion, I'm not quite willing to run that on the real robot, right? So, I think that's cool if you pull, where's Emma? I don't want to, yeah, but, I think it's cool, but I wouldn't want my plates flying across the room. Right, so, and in practice, it was the DARPA challenge for me that sort of made me more conservative, right? I was afraid to run our trajectory optimization, our nonlinear trajectory optimization on the real robot when the chance of failure was too high, the cost of failure was too high. And that has taken me down this much more conservative route, admittedly, of trying to solve with reliable guarantees. Okay, but the MIQP is hard. There's a computational bottleneck. Mixed integer problem has lots of binary variables. The naive implementation is 2 times the number of potential contact pairs times the number of time steps. That's bad. That's just the binary variables. Some of that, I think we should, I think that's a problem of our transcription, but it's hard to get around. We're not yet close to solving this at real-time rates. So there's a couple things we're trying to do to make that better. 2 broad approaches. We've got a lot of work on trying to make real-time contact MPC work, and we've got work on approximate explicit MPC, and I'll tell you about both of them quickly here. So the first thing is the way you transcribe your contact problem into an MPC into an MIQP problem matters a lot, right? It matters in the number of decision variables, and there's some well-known lessons from disjunctive program that if you have to get it right in order to make more efficient MIQPs. So there's a rich background in hybrid MPC, and the performance of these solvers depends completely on how the branch and bound algorithm works, which depends on the number of binary variables, but also the tightness of the convex relaxations as you descend the branch and bound tree. So we've done a lot of work about thinking about the specific formulations you get out of contact and making maximally tight and efficient formulations for MPC. And Tobia, who's here, has done some nice work on understanding that tightness, and there's a trade-off between using these convex hull formulations and getting too many binary variables, but there seems to be a sweet spot where for every time step you group the variables and do a convex hull relaxation, but leave the other variables distinct. There's a sweet spot, and I'd encourage you to look at the paper to see some of the details on that. The other key idea is using these perspective formulations to include the objective function in the formulation to further tighten the relaxation. So in practice, what that means is we can take non-trivial contact problems, but still toy problems. They're complicated dynamics, but low-dimensional and small, but solve them to global optimality. And it's just a different space to be in when your solver ends and you know it's done the right thing or it's reported infeasible. And that's getting us from problems with original formulations that were like an hour, really bad, to something that's maybe tolerable, 320 seconds or something like that, but we're not yet at real-time rates. Okay, but now Tobia is working on doing warm starting for branch and bound, and it's actually really, really good. Okay, so the big idea here, we're solving nearly identical optimization problems on every time step. The MPC, warm starting should be great for MPC, but somehow people haven't really figured out how to warm start branch and bound solvers. People do lots of worm starting inside a branch and bound solve for one solve. But then if you've got a branch and bound tree and you've moved the problem data a little bit and you're going to solve an almost similar problem, how do you warm start that new set of solutions? Okay? And it turns out that if you look at the dual of each of the subproblems, then you can, with some understanding of what how the problem data is going to move, you can just use the dual to move your lower bounds from one time step into conservative lower bounds for the next time step, which makes sense. And what that means is that you can restart your solve tree and rapidly discard most of the tree, okay? And in practice, that means we go from solving thousands of, let me just jump to the punchline on that. We transition from solving sort of thousands of QPs for a single problem, like a cart pole smacking its head against the wall, to something like you solve less than 10 on each time step. Your first solve is expensive, but then you're basically solving at very high rates your MIQP afterwards. And I think that just has to be the right solution. And in practice, when we're solving problems like what Emma was showing you, I mean, it's the contact sequence that changes. You should be able to think about what's nominally going to happen, and very small deviations from that original plan should work. Warm starting should be extremely good, and we're finally getting our head around that. Also, approximate explicit MPC. So explicit MPC, many of you know, gives us sort of an understanding, more sort of than the algorithm. The algorithms blow up very quickly, but it gives us a lot of understanding about the form of what the optimal policy and optimal value function looks like for these problems. Okay, for constrained linear optimization, it's a pretty but complicated picture. The things are piecewise affine, polytopic in the simple case. But when you go to the hybrid case, you lose some of those properties. We still understand more about the structure, but not enough to be. It's extremely complicated solution. So the problem is, given our local understanding of the structure of the optimal policy, can we approximate that with simpler functions? We don't actually need the optimal solution, but we'd like something to be at least strictly feasible. Okay, and the short answer is yes, you can. There's a fun, I think there's a lot more work to do here. But if you think about solving, if you solve an MIQP once, you lock in the integer variables. You're left with a quadratic program. You can think about what's the feasible set of that quadratic program. That covers a huge portion of state space. Computing the exact feasible set of the QP is expensive, but an inner approximation can be done pretty quickly. And then you can think of it as a set cover problem where you try to cover the state space with a handful of quadratic programs that you have to solve. Okay, so the details, I'm sorry, I'll go through quickly, but the details, I think there's a lot of promise in thinking about approximate explicit MPC in ways that can still guarantee closed loop stability. Okay, there's Emma, sorry. And our experiments on hardware of using this type of formulation are still modest, but we're getting to the point where we're doing these first sort of feedback control using the principled approaches on hardware. This one in lab, when you see this marker, that's a cheat. And to be clear, that's a cheat we're using for these initial experiments because we assumed full state feedback and everything I just said about the MIQPs. The original example did not. I want to just make that clear. You can also think about these explicit MPC solutions, or the MIQP, as being an oracle for doing learning control. If you believe that the right way to represent your policy is as a deep neural network, or if you want to represent your value function as a deep neural network, then wouldn't it be nice to basically have a way to sample from the true optimal policy, even if it's expensive, offline? I'm just making sampling data. You could do this and sort of populate the solutions for your learning control. So we've been playing with that kind of idea too. The mixed integer convex optimization is global but slow, but there's a nice idea, which is that you can in intermediate solutions of your branch and bound, you actually get upper bounds and lower bounds on the true optimal solution. So if you're trying to fit the value function, then you can actually train a neural network with a hinge loss that says that the true value should be inside this interval. And actually with relatively quick solutions to your MIQP, you can get intervals on the optimal solution very quickly, okay? And that's solved pretty hard problems. Okay, so that was just that was hopefully a call to action that I think we could do a lot more in sort of explicit solutions of these hard problems. And that feels like something that should be within our grasp. There's a couple things that come out of this, though. So, in the way that the controls folks are, look at uncertainty representations. I love polytopic uncertainty. I love ellipsoidal uncertainty, whatever. I want to just make sure we contrast that with how the reinforcement learning people have started looking at this in a very healthy way. they've been throwing much more generic sources of uncertainty into the simulation, right? They're randomizing lighting conditions, number of objects, things like this. And I think that's a call to action for control. It seems like there's something good happening there. Can we bring our robust control formulations closer to these sort of specifications of uncertainty? But I will note that actually those are still distinct from what's happening sort of in the real world, which is that, so for instance, if you're developing an autonomous car, the way you write your requirements is hard, but it's typically about finding corner cases. Who's found the most corner cases and has a bunch of list of scenarios. So I think there's a call to action also to bring our different ways of representing uncertainty and problem formulations together, and I think robust control needs to grow in the direction of solving those harder specifications. Okay, so basically we're working hard on control through contact. There's a lot more to do. I think there's simpler representations of those optimal functions, and I don't need optimal. I think dynamic state feedback is a candidate, and I think output feedback is an important candidate. So let me talk a little bit more about output feedback. So when you look at this, like I said, this is only using raw sensor data. It's not tracking with motion capture and everything. So its information about the plate is actually very limited. It's only from cameras, which are noisy and can be occluded and the like, and local force sensors. Okay, but somehow it's quite robust. So I think this challenges, I mean, we haven't done enough work in controls on output feedback, right? But the problem is manipulation really breaks that model pretty quickly. Like, what's the state space of that system? Do I really need to know the pose of the 15th mug in the bottom corner of the bin in order to make my first control decision? Yeah, probably not, right? Does full state feedback even make sense, right? With my controls hat on, you could say, well, I should be doing model order reduction, right? I should have a reduced state estimate and I can do control. But at some point, that doesn't feel like the right solution. Maybe these problems of subspace, they're certainly task dependent, which is not our standard model, not impossible for model order reduction, not the standard model order reduction. And I think there's some representational learning that's happening in learning theory that could be very good for these types of problems. So let's think about, the output feedback problem, to be clear, is almost exactly what we've talked about with the LQR problem, but the simplest form of it is I have my linear dynamical system, and I'm trying to find a linear feedback of the output now, right, if I'm just searching over K. And we know that problem's hard. The stabilizing K form a disconnected set, so Miri and I were talking about it last night. Clearly that local optimization on K is not going to work in this case from any initial stabilizing K. But it's a known hard problem. That doesn't mean we shouldn't be working on it, right? Dynamic output feedback is important. LQG is a special case. The problem is that my output feedback problem goes through cameras, right? So Manfred, I do have a model, but my model includes a full-on game engine in the middle of it. So it's hard to use all of my best tools, although we're trying. So let me tell you a few of our representational questions to get there. And we're trying to build on the advances in deep learning for perception to get us to this intermediate representation that can close the gap from sensors to actions. So in deep perception, we've seen classification work, detection work, segmentation work, key point detections, more recent, getting these dense descriptions. But most of these initial problems, although the data sets are fantastic, they're not quite enough to use for manipulation. So the question is, what do you need in your representation in order to do more from manipulation? Another set of advances that's been going simultaneously is SLAM, works incredibly well. And so can we take these advances and put them together to make something work very well? And the answer is that we've been working on these dense descriptors, which turns out I will have to talk about very quickly, to learn correspondences. Let me just say the quick version. We can have a robot self-supervised learn by taking many images of an object, a brand new object. By doing dense reconstruction of the geometry, we can self-supervise. We can say the image you saw here it sees this particular pixel. That's the same pixel you see here. And you can set a pixel-wise contrastive loss and learn a correspondence between those two images, self-supervised, without any human labeling. And this has given us rich specifications that allow you to have sort of surprisingly robust representations of even deformable objects. This is just a simple way to visualize the representation. If the colors stay consistent on the object, then we've done a pretty good job of understanding that object in this dense descriptor space. Okay? And in practice, that allows us to do things like you click on this object once, and you can pick it up from any, from many different orientations, many different configurations, because we've got somehow enough semantic understanding of the object and geometric understanding of the object simultaneously to do something more than just object recognition. And I'll close with just, we have some versions of this demo here that, that will, for instance, put anybody's shoe on the rack. And I would encourage you, this is Ben's commitment here, if you would like to come up between 12 and 2, I guess, is our next break, and if you have a shoe, then you're welcome to put us to the test. Take your shoe off, put it on the rack, and I'm pretty sure we're going to do some non-trivial manipulation with it. We found some pretty strange shoes when I've said things like that before, but I think it's pretty good. Okay, so I believe, in conclusion, I believe in data. I think data clearly has a huge role to play. I think high-dimensional statistics have a lot to tell us. It's already an obvious win for perception, and control cannot continue to ignore perception. We have few robots now, but we're going to have many robots, and fleet learning is surely coming. But I still like F equals MA. For RL, sample efficiency and robustness are fundamental concerns. I think we have stronger synthesis results when we use those models. We have to be pragmatic, too. I think I'm going to write simulators just to do the engineering. And if I've got the models, you better believe I'm going to use them and write the best structured optimization we can possibly write. All right.
Questions? Who's raising their hand? I'm blinded by the light over here. Oh, it's a question in the front. Question in the front.
Over
Your mic isn't on.
How do I?
You're good now.
Magic. There we go.
You need connection. Okay. Is it on now? So I think we can all agree that we need some kind of mixed integer or relaxed thing to enumerate over contact modes. And actually, the GDD thing I showed is exactly that, but no guarantees 100 microseconds. Question is, do you really have to do that over time? So in your worst case situation, 360 seconds for the whole trajectory, that's bad. But could it be that we can get away with the simple value function approximation, maybe even quadratic, and then do only one step of that, or maybe 5 steps or whatever, but something much shorter? And how short is that? I think that, to me, that's the big question. If we cannot get away with the short time horizon, that's bad. We should go home.
Yeah. No, so just to make sure, in case people didn't hear that, he says, why would you, mixed integers, fine. Mixed integers over 300 seconds or horizon or something seems intractable. We shouldn't do that. Of course, you can use the standard understanding from MPC to write a control Lyapunov function that captures as my terminal set. And the question is, can you get away with just a very short horizon? For instance, if you could get away with maybe 5-step horizon and then a clever control Lyapunov function, then you should be good, and you'd have the rigorous reachability and the like. I think that's part of the answer. I also think that the structure that Explicit MPC tells us about the mixed integer problem is, it looks more complicated than it should be. So I actually think that there's very simple approximations of it, which look like the controllers that C1 and others have been writing on the, I think very simple state machines are actually very close to the solutions that we're getting out of that. We're just representing them the wrong way by thinking about them as static feedback. So I think there's alternative representations of even the harder problems that will make them much more expressible. Yeah?
Thanks for the talk. My question is about the fact that one of the arguments of RL is that we don't have to use domain-specific knowledge when we are designing our reward functions or algorithms, right? And there are methods that solves really hard manipulation task that contains contacts and long horizon planning types, right? But on the model-based methods, we have to actually know the domain-specific knowledge to be able to write our cost functions and constraints. What are your thoughts on this, this comparison?
Okay, so I might disagree with the basic premise that we have RL solutions that solve manipulation problems. Sorry. What you mean by solve manipulation, depends. I think doing it in a simulation is much easier than doing it in reality. And doing it without noise and other things, I think real sensors and partial observability and perception are actually the dominant problem in manipulation. Control has to be enough, but it has to be attached, grounded firmly in perception. So I think the cost functions, the problems are the same. I would go with Emo on this one. I think if you have a model, whatever cost function it is, you should use every tool at your disposal, including calculus, to take those gradients. I also think the more we can understand about the class of the policies that we want to be searching over, the better. I would love to find out that there's a way to parameterize that, whether it's over-parameterization or whatever, for which policy gradient works. Like Miriam's result yesterday was awesome. If I could say that for a contact problem, I would be in heaven. I don't have it yet.
All right, one last question, please.
So I'm convinced that number of parameters is no longer a good metric for simplicity. So I guess the amount of data required to obtain it is maybe a better metric. But I think maybe we'd agree that the number of faces in the polytopic representation of the explicit MPC solution is not simple. I agree that just defining simplicity is hard, but I see beautiful controllers that are written with a handful of parameters that are written in state machines and the like, that have guards based on contact forces that work very well, better than my approximate optimal solutions. So in that sense, I know that there are representations out there that are capable with even handfuls of parameters, and they're dynamic controllers, which I don't know how to find, but perform very well.
All right, let's thank Russ again for a great talk.